What if you could write standard numpy and pandas code, but have it run on a distributed computing grid for incredible parallel processing right from Python? How about just splitting the work across multiprocessing to escape the limitations of the GIL right on your local machine? That's what Dask was built to do. On this episode, you'll meet Matthew Rocklin to talk about its origins, use cases, and a whole bunch of other interesting topics. This is Talk Python to Me, episode 207, recorded February 20th, 2019. Welcome to Talk Python to Me, a weekly podcast on Python, the language, the libraries, the ecosystem, and the personalities. This is your host, Michael Kennedy. Follow me on Twitter where I'm at mkennedy. Keep up with the show and listen to past episodes at talkpython.fm, and follow the show on Twitter via @talkpython. Hey folks, a quick announcement before we get to our conversation with Matthew. People have been enjoying the courses over at Talk Python Training for years now, but one shortcoming we've been looking to address is to give you offline access to your content while you're traveling, or if you're just in a location with spotty internet speeds. We also want to make taking our courses on your mobile devices the best they can be. That's why I'm thrilled to tell you about our new apps, which solve both of these problems at once. Just visit training.talkpython.fm/apps and download the Android version right now. The iOS version is just around the corner, should be out in a week or so. You'll have access to all of your existing courses. But we've also added a single tap feature to allow you to join our two free courses, the Responder Web Framework mini course and the MongoDB Quick Start course. So log in, tap the free course, and you'll be right in there. Please check out the apps and try one of the free courses today. Now, let's talk Dask with Matthew. Matthew, welcome to Talk Python to Me.
Thanks, Michael. I've listened to the show a lot. It's really an honor to be here. Thank you for having me.
It's an honor to have you as well. You've done so much cool work in the distributed computing space, in the data science and computation space. It's going to be super fun to dig into all that, and especially dig into Dask. But before we get to that, of course, let's start with your story. How'd you get into programming in Python?
So I got into programming originally actually on a TI basic calculator. So I was in math class plugging along. Spent my few thousand hours not being a good programmer there. Picked up some C++ in high school, did some MATLAB and IDL and C# in college, did some engineering jobs, did some science. And then in grad school, just tried out Python on a whim. I found it was all of those things at the same time. So it was
awesome.
So it was fun to work in object-oriented mode, like with C#. It was fun to do data analytics, like with MATLAB. It was fun to do some science work that I was doing in astronomy at the time, like with IDL. So it was sort of all things to all people. And eventually I was in a computer science department, and I found that Python was a good enough language that computer scientists were happy with it, but also usable enough language that actual scientists were happy with it. I think that's probably where Python gets a lot of its excitement, at least on the sort of numeric Python side.
I think that's a really nice insight, and it sounds like a cool way you got into programming. I feel like one of Python's superpowers is it's kind of what I think of as a full spectrum language. You can make it what you need it to be at the beginning, but like you said, professional developers and scientists can use it as well. And you kind of touched on that, right? Like you can use it like C#, or you can use it like MATLAB, or you can kind of be what you need it to be. But if you need more, it's not like, well, now you go write in C++. It's just like, well, now use these other features.
Yeah, definitely. I'd also say it has a lot of different parts to it. Before there was the web programming community, and there was a community that used it kind of like Bash, like a sysops community, and there was the scientific community. I know those are all kind of the same, and it's really cool to see all those groups come together and use each other's stuff. You see people using scikit-learn inside of a Flask app deployed with some other Python thing.
Ansible or something, right? Yeah, for sure.
And the fact that all those things were around makes it sort of the cool state that it's in today.
Yeah, it's just getting better, right?
But it was already good. It's just like connecting all the good parts.
Exactly. It's the interconnections are building a little bit stronger across these disciplines, which it's kind of rare, right? There's not that many languages and ecosystems where that happens, right? Like think of Swift for iOS, right? Swift is a pretty cool language. It has some issues that I could take with it, but it's pretty cool. But it's not also used for data science and for DevOps, right? It's just not.
Right. Yeah.
That's pretty cool. Also, you said you did some IDL. It sounds like you were doing astronomy before, right?
Yeah, this is just in undergrad. I was taking some astronomy courses. It was fun, though, because I knew how to program, and I was just really productive as a scientist because I was, fluent in programming. That ability to be more productive is really what took me away from science and towards computer science. but in service of science. So that was my experience.
Now you're building these platforms where like legitimate world-class science is happening.
Yeah, no, it's cool.
Right? You must be really proud, right? To think of like what people are doing with some of the software you're building and you're collaborating
Yeah,
on.
the software that all of us build. And it's definitely very cool. It's very satisfying to have that kind of impact, not just in one domain, but across domains. And, get to work with lots of different kinds of people every day that are solving, I think, high impact problems. And yeah, that's definitely a strong motivator for me.
Yeah, I'm sure it is. It's, programming is fun, but it's really not fun to work on a project and have nobody use it. But to see it thrive and being used, it really is a gratifying experience.
Yeah, I'll go so far as to say that programming is no longer fun. It's just the way we get things done. And seeing them done, as you say, is really where a lot of the satisfaction comes from.
Yeah, it's cool. So how about today? What are you up to these days? You were, put it past tense, you were doing a lot of stuff with Anaconda Inc., previously named Continuum, but same company. Mm-hmm. But not recently you've made a change, right?
Yeah. So I like to say it's the same job, just a different employer. Yeah. So I guess my job today is a few things. I work in the open source numeric Python ecosystem. So this is usually called like SciPy or PyData. And I mostly think about how that system scales out to work with multi-core machines or with distributed clusters. I usually do that with a project called Dask. That's maybe like the flagship project that I help maintain, but I'm just generally active throughout the ecosystem. So I talk to the NumPy developers, the pandas developers, scikit-learn and Jupyter developers. I think about file formats and protocols and conventions. There are a few of us.
Networking.
Yeah, lots of things. So generally in service of those science use cases or in business use cases, there's tons of things that go wrong. And I tend to think about whatever it is needs to get handled. But generally, I tend to focus on Dask, which I suspect we'll talk about more today.
Yeah, a tiny bit. So speaking of Dask, let's set the stage, talk a little bit about, why does Dask exist and so on. And I guess maybe start with a statement that you made at PyCon, which I thought was pretty interesting. And you said that Python has a strong analytical computation landscape, and it's really, really powerful, like pandas and numpys and so on, but it's mostly focused on single core computation and, importantly, data that fits into RAM. You want to elaborate on that a little?
Sure. So everything you just said, so all of those libraries, so NumPy and pandas and scikit-learn are loved today by data scientists because the APIs they do everything they want them to do. They seem to be well tailored to their use cases, and they're also decently fast. Right, so they're not written in pure Python. They're written in C, Fortran, C++, Python, LLVM, whatever.
Right. And so much of the interaction is like, I have the data in Python, I just pass it off. Or maybe I don't even have it in Python. I have like a NumPy array, which is a pointer to a data down in C level, which I then pass that off to another part. And then internally down in C, it cranks on it and gives it back like 5 or something, right? Like, so it's a whole, I think the whole story around performance and is Python slow, is Python fast? Like it gets really interesting really quick because of those types of things.
Yeah. So we have really nice usable Python APIs, which are kind of like the front end to a data scientist. And that's hitting a back end, which is C++ Fortran code, which is very fast. And that combination is really useful. Those libraries also have like now decades of expertise, PhD theses thrown into them, just tons of work to make them fit. And people seem to like them a lot. And it's also not just those packages. There's hundreds of packages on top of NumPy, pandas, scikit-learn, which do biology or do signals processing or do time series forecasting or do whatever. And there's this ecosystem of thousands of packages. But that code that's very powerful is really just powerful on a single core, usually, on data that fits in RAM. So as sort of big data comes up or as these clusters become more available, the whole PyData SciPy stack starts to look more and more antiquated. And so the goal that I was working on for a number of years and continue to work on is how do we elevate all of those packages, NumPy, pandas, scikit-learn, but also everything that depends on them, to run well on distributed machines, to run well on new architectures, to run well on large data sets. How do we sort of refactor an ecosystem? And that's a really hard problem.
That's a super hard problem. And it's, I think, one of the challenges that PyPy, the JIT compiled alternative to CPython has such, I think that would have really taken off had it not been for, yes, we can do it this other way, but you have to lose NumPy, or you have to lose this C library, or you lose the C speedups for SQL Alchemy or whatever, right? You're trying to balance this problem of like, I want to make this distributed and fast and parallel, but it has to come along as is, right?
Right. Yeah, we're not going to rewrite the ecosystem. That's not a feasible project today.
Right. I mean, theoretically, You could write some alternate NumPy, but people trust NumPy. And like you said, it's got so much polish. It's insane to try to recreate it.
Yeah, it also has, even if you recreated it, there's a lot of weight on it. A lot of other packages depend on NumPy in very arcane ways, and you'd have a hard time reproducing all of those.
Right. Yeah. It's like boiling the ocean or trying to boil the ocean, pretty much. Okay. And then, so that's the problem is like we have problems that are too big for one machine. We have great libraries that we can run on one machine. How do you take that ecosystem and elevate it in a way that's roughly the same API, right? We had certain things like that, right? Like Spark, for example, is one where you can do kind of distributed computation, and there's Python interactions with Spark, right?
Yeah, definitely. But Spark is, again, going down that rewrite path, right? Spark is not using NumPy or pandas. They're rewriting everything in Scala, and that's just a huge undertaking. Now, they've done a great job. Spark is a fantastic project. If Spark works for you, you should use it. But if you're used to pandas, it's awkward to move over. Most good Python pandas devs that I know who move to Spark eventually move to Scala. They eventually give up the ecosystem and they move over. And that makes sense given how things work.
Right.
But if you wanted to say...
Because if you're going to work there, you might as well be native in that space, right?
But if you wanted to say use NumPy, like there is no Spark NumPy, nor is there a Spark SciPy, nor is there a Spark time series prediction.
Everything built on it.
Yeah. So Spark really handled sort of the pandas use case to a certain extent and like a little bit of the scikit-learn use case. But there's this other sort of 90% of the ecosystem that's not handled. And that's where Dask tends to be a bit more shiny.
Right. And I don't do much with Spark, so you'll have to keep me honest here. But isn't Spark very like map reducey? It has a few types of operations and pipelines you can build, but you can't just run arbitrary code on it, right?
Yes and no. So yes, underneath the hood, from like a distributed systems point of view, Spark implements sort of the same abstraction as MapReduce, but it's much more efficient and it's much more usable. The APIs around it are much nicer. So if you do something like a group aggregation, that is sort of a mapping and then a reduction under the hood. And so as long as you sort of stay within the set of algorithms that you can represent well with MapReduce, Spark is a good fit. Not everything in the sort of the PyData SciPy stack looks like that, it turns out. And so we looked at Spark early on and, hey, can we sort of use the underlying system to parallelize out PyData? The answer came back pretty quickly, no. It's just not flexible enough.
Yeah. And, I love that this format is audio, but for this little part, I wish we could show some of the pictures that you've had and some of your presentations and stuff, because the graphs of how all the data flows together is super, super interesting and complicated and sort of self-referential and all sorts of stuff.
Yeah,
right?
no, those visuals are really nice. And it's nice that they're built in. You get a good sense of what's going on.
Yeah, it's cool. All right, so let's talk about Dask. You've mentioned it a couple of times. Dask is a distributed computation framework focused on parallelizing and distributing the data, the data science stack of Python, right?
Yeah. So let me describe it
roughly
I'll from a 10,000 foot view first, and then I'll dive in a little bit. Mm-hmm. So from a 10,000 foot view, the tagline is that Dask scales PyData. Dask was designed to parallelize the existing ecosystem of libraries like NumPy, pandas, and scikit-learn, either on a single machine, scaling out from memory to disk using all of your cores, or across a cluster of machines. So what that means is if you like pandas, you like NumPy, and you want to scale those up to many terabytes of data, you should maybe investigate Dask. So diving in a little bit, Dask is kind of two different levels. I'll describe Dask at a low level first and then at a high level. So at a low level, Dask is a generic Python library for parallel computing. Just think of it like the threading module or like multiprocessing, but just more. There's more sophistication in there. It's more complex. It handles things like parallelism, like task scheduling, load balancing, deployment, resilience, node failover, that kind of stuff. Now, using that very general purpose library, we've built up a bunch of libraries that look a lot like PyData equivalents. So if you sort of take Dask and NumPy and smash them together, you get Dask Array, which is a large scalable array implementation. If you take Dask and pandas and squash them together, you get Dask Data Frame, which uses many pandas data frames across a cluster, but then can sort of give you the same pandas API. So it looks and feels a lot like underlying sort of normal libraries, NumPy or pandas, but it scales out. So today when people talk about Dask, they often mean Dask Data Frame or Dask Array.
Yeah. So just to give people a sense, like this, when you interact with one of these, say, Dask arrays, it looks like a NumPy array. You treat it like a NumPy array mostly. But what may actually be happening is you might have 10 different machines in a cluster. And on each of those machines, you might have some subset of that data in a true NumPy array, right? And that's they know how to coordinate operations. So if you do like a dot product on that with some other bit, it can figure out the coordination and communication across all the different machines in the cluster to compute that answer in a parallel way. But you think of it as like, well, I just do a dot product on this array and we're good, right? Just like you would in NumPy.
That's exactly correct. Yeah, so Dask is like a very efficient secretary. It's doing all the coordination work. NumPy is doing all the work on every node. And then we've written a lot of parallel algorithms around NumPy that teach you how to do a big matrix multiply with a lot of small matrix multiplies. Or on the pandas side, a big join with a lot of smaller joins.
That sounds like a lot of coordination and a challenging problem to do in the general sense.
It's super fun.
The general solution of that. Yeah, I bet it is. A lot of linear algebra and other types of stuff in there, I'm guessing.
Sure, or a lot of pandas work, or a lot of machine learning work.
Yeah.
Or a lot of other work. So I want to point out here that the lower level Dask library, the thing that just does that coordination, is also used separately from NumPy and pandas. And I'm sure we'll get to that in the future. But so Dask is sort of this core library that handles parallelism. You can use it for anything. There's also like a few big uses of it for the major PyData libraries.
Yeah. We have Dask array and we have Dask data frame and so on. And these are really cool. And we said the API is really similar, but there's one significant difference. And that is that everything is lazy, right? Like a good programmer.
Sure. So Dask array and Dask data frame do both do lazy operations. And so at the end of your, you do data frame, you do read parquet, filter out some rows, do a group aggregation, get out some small result. You'll then call .compute. At the end of that, there's a method on your Dask data frame object, and that will then ship off the sort of recipe for your computation off to a scheduler, which will then execute that and give you back a result, probably as a pandas data frame.
Right. So there's two major parts here. One is the data structures that you talked about, and the other is the scheduler idea, right? And those are almost two separate independent things that make up Dask.
Two separate code bases even.
Okay. This portion of Talk Python to Me is brought to you by Linode. Are you looking for hosting that's fast, simple, and incredibly affordable? Well, look past that bookstore and check out Linode at talkpython.fm/Linode. That's Linode. Plans start at just $5 a month for a dedicated server with a gig of RAM. They have 10 data centers across the globe, so no matter where you are or where your users are, there's a data center for you. Whether you want to run a Python web app, host a private Git server, or just a file server, you'll get native SSDs on all the machines, a newly upgraded 200 gigabit network, 24/7 friendly support even on holidays, and a 7-day money-back guarantee. Need a little help with your infrastructure? They even offer professional services to help you with architecture, migrations, and more. Do you want a dedicated server for free for the next 4 months? Just visit talkpython.fm/Linode. I want to dig into the schedulers because there's a lot of interesting stuff going on there. One thing that I think maybe might be worth digging into a little bit for folks is this demo that you did at PyCon around working with, basically you had this question you want to answer is like, what is the average or median tip that a person gives to a taxi cab driver plotted by time of day, like Friday evening, Monday morning, and so on. And so there's a huge data set. Maybe you tell people where to get it, but it's the taxi cab data set for some year. And it's got like 20 gigs on disk and 60 gigs in memory. Now, I have a MacBook Pro here that's like all knobs to 11, and that would barely hold half of that data, right? So like even on a high-end computer, it's still like I need something more to run this because I can't load that into memory.
Well, to be fair, actually, that's not by big data standards. It's actually pretty small. People use Dask on 20 terabytes rather than 20 gigabytes pretty often. But you're right that it's it's awkward to run on a single machine.
Yeah, you can do a lot of paging.
Yeah, it's a pretty easy data set though to run in a conference demo just because it's pretty interpretable.
Yeah.
Yes.
Everyone can immediately understand average tip by time of day and day of the week.
Yeah, so it's a good demo. I'll maybe talk through it briefly here, but I encourage people to look at the PyCon. Yeah. There's probably PyCon 2017, I think, for Dask.
Yeah, and I'll put a link to the talk in the show notes.
So in that example, we had a bunch of CSV files living on Amazon S3 or Google Cloud Storage. I don't remember which.
Yeah, Google Cloud Storage.
And you could use the pandas read CSV function to read a bit of those files, but not the entire thing. But if you try to read everything, it would fill up RAM and pandas would just halt. And that's kind of the problem we run into in PyData today when we hit big data. Everything's great to run out of RAM, then you're out of luck. So we sort of switched out the import for pandas for Dask data frame, called the Dask data frame read CSV function, which has all of the same keyword arguments of pandas read CSV, which if you know pandas are numerous. Then sort of reading one file, we sort of give it a glob string. We asked it to read all the files. Yeah, we did normal pandas API stuff. I think we filtered out some bad rows or some free rides in New York City that we had to remove.
Mhm.
We made a new column, which is a tip fraction. We then used pandas datetime functionality, I think, to group by the hour of the day and the day of the week. And if you know pandas, that API is pretty comfortable to you.
Just the data's too big.
Yeah, it was the same experience. Pandas. We switched out the import. We put a star in our file name to read all the CSV files. We might have asked for a cluster. So we might have asked something like Kubernetes or Yarn or Slurm or some other cluster manager to give us a bunch of Dask workers. That one's probably using Kubernetes because it's on Google. Those showed up. So Google was kind enough to give us virtual machines. We deployed Dask on them. And then we hit compute. And then all of the machines in our cluster went ahead and they probably called little pandas read CSV functions on different ranges in those CSV files coming off of Google Cloud Storage. They then did different group by operations. They did some filtering operations on their own. They're probably somewhat related to the ones that we asked them to do, but a little bit different. They had to communicate between each other. So those machines had different pandas data frames. They had to share results back and forth between each other. If one of those machines went down, Dask had to ask for a new one or had to recover the data that machine had. And at the very end, we got back a pandas data frame and we plotted it. And I think the punchline for that one is that the tips for 3 or 4 a.m. are absurdly high. It's 40% or something like that.
Yeah. Did you have any insight to why that is? Do people know?
I mean, the hypothesis is that it's people coming home from bars. I was actually giving this same demo at a conference once, and someone was like, "Oh, filter out all the short rides, and I'll bet it goes away." And so you did that, and the spike does go away. And so it's probably just people getting $5 cab rides from the bar. And we were looking at tip fraction, which is sort of going to have a lot of noise.
Right.
But it was fun because this guy said, "Hey, try this thing out," and he knew how to do it. He had never seen Dask before. He had just known pandas before. Gave him the keyboard. He typed in the pandas commands and it just worked. We got new insight out of it. And so that sort of experience shows us that a tool like Dask Data Frame gives us the ability to do pandas operations, to extend our pandas knowledge, but across a cluster. That data set could have been 20 terabytes and the same thing would have worked just fine. You would have wanted more machines, but it would have been fine.
Wait, or one more time.
One more time. Yeah. So Dask also works well on a single machine just by using small RAM intelligent ways.
Oh, it does. Okay. So it can be more efficient. You could give it a ton of data, but it can realize I can't take it all in one big bite. I got to eat the elephant sort of thing.
Yeah. So if you can run through your computation in small RAM, Dask can usually find a way to do so. And so that's actually Dask can be used on clusters. And that's the flashy thing to show to people at a PyCon talk. But most Dask users are using just their laptops. So for a long time, Dask actually just ran on single machines for the first year of its life. We built all the parallel algorithms, but didn't have a distributed scheduler. And there people just wanted to sort of stream through their data, but with pandas or numpy APIs. So people were dealing with 100 gigabyte data sets on their laptops pretty comfortably.
Oh, that's interesting. I didn't realize that was a thing it could do. That's cool. Could it be used in the extreme, if I've got a really small system with not much RAM at all, I'm thinking little IoT things. Could it let me process not big data, but normal data on a tiny device?
Sure. Depending on how much data or how much you're looking for, sure.
Yeah. Okay. Interesting. That's a super cool feature. Now, one of the first things that struck me when you ran this, obviously you've got all these machines. I think you had 32 systems with 2 cores each when you ran the demo, and it went really quickly, which is cool. I expected it to come up with a graph and you could say, run it. Look, we can't even run it locally. Here it is in 10 seconds or something. But instead, what I saw when you did that was there's a beautiful graph that's live and animated describing the life of your cluster and the computation and different colors meaning different things. Can you describe that diagnostic style page and so people know?
Yeah, sure. It's hard to describe a picture, much less an interactive dashboard. But yeah, so maybe I'll describe a little bit of the architecture of Dask first, and I'll make this a bit more clear.
Okay.
So Dask has a bunch of workers that are on different machines that are doing work, holding on to data, communicating with each other. And then there's a centralized scheduler, which is keeping track of all those workers. This is the foreman at a job site, maybe. Of all these workers, telling the workers what to do, telling them to share with each other, et cetera. And that foreman, that scheduler, has a ton of information about what all the workers are doing, all the tasks that are being run, the memory usage, network communications, file descriptors that are open on every machine, et cetera. And in trying to benchmark and profile and debug a lot of Dask work, we found that we wanted access to all that information. And so we built this really nice dashboard. And so, it tells you all that information. You saw one page at that demo, but there are 10 or 20 different pages that have different sets of information. So there's just a ton of state in this scheduler, and we wanted to expose all that state visually. This ends up being it was originally designed for the developers, but it ends up being critical for users because understanding performance is really hard in a distributed system, right? Our understanding of what is fast and slow on a single machine gets totally turned around when you start adding concurrent access to disk and network communications and everything. So yeah, it's a live dashboard. We used Bokeh. That's a Bokeh server application to build it.
Mm-hmm.
So it's got, it's updating at something like 100 milliseconds frame rates. So it looks live to the human eye. Yeah, it's showing you progress. It's showing you every task that gets done and when it gets done and where it gets done. It's showing you memory use on all different machines. You can dive in. You can actually get like line-by-line profiling statistical information on all of your code.
Will that coordinate across machines? So like this function is taking this long, but actually it's summing up the profiling across all the cluster?
Yep. So the scheduler is just aware of everything, and the workers are all gathering tons of information. There's tons of diagnostics on that machine. Yeah, so maybe a way to say this is that in order to make good decisions about where to schedule certain tasks, Dask needs to have a bunch of information about how long previous tasks have taken, the current status everywhere. And so we've gotten very, very good at collecting telemetry and keeping it in a nice index form on the scheduler. And so now that we have all that information, we can just present to people visually.
Might as well share.
Yeah. I find myself sometimes using Dask just on sequential computations just because I want the dashboard. Like I don't want parallelism. I just want the dashboard. It's just the best profiler I have.
It is a good insight into what's happening there. That's super cool. And I love that it's live. So it seems really nice. I was surprised at how polished that part of it was.
That is honestly just due to Bokeh. If people, if they like dashboards, go look at Bokeh server. I didn't know any JavaScript. I didn't know about Bokeh before. It was super easy to use. I integrated it into my application. It was clean. It was nice. And it looks polished, as you said.
That's super cool. Now, you did say that you can run Dask locally, and there's a lot of advantages to doing that, as you already described. But it's super easy, right? Maybe just describe, like, it's just a couple of lines to set up a little mini cluster running on your system, right?
Yeah, so it's even easier than that. But yes, so if you do from Dask, so if you, first of all, you would pip install Dask or const install Dask. It's a Python library, it's pure Python. You would then, if you want the sort of the local cluster experience with the dashboard and everything, you say from Dask.distribute import client. And then you create a client, which with no arguments. And it would create for you like a few workers on your local machine and a scheduler locally. And then all the rest of your Dask work would just run on that. You also don't need to do that. You can just import Dask, and there's a thread pool waiting for you if you don't set anything up. So a lot of people, again, don't use the distributed part of Dask. They just use Dask locally. And Dask can operate just as a normal library. Spins up a thread pool, runs your computations there, and you're done. So there's no actual setup you need to do.
Right.
Sorry, there was a great tweet maybe a few weeks ago. Someone was using the Xarray library. Xarray is a popular library for array computing in like the geoscience world. Someone says like, yeah, someone was recommending Xarray and Dask on Twitter, and someone says, yeah, I've heard about Xarray, use it all the time, it's great. Never heard of Dask though. Don't know what you're talking about. And it was hilarious because Xarray uses Dask under the hood. The guy had just never realized that he was using Dask. So that's a real success point.
Yeah. If you don't have to poke your head up and like make it really hard and obvious that this thing is part of it, right? That's great.
Dask had disappeared into being just infrastructure.
Yeah. So another thing that I thought was a super cool feature about this is you were talking about some kind of working with a really big tree of data, right? And you start processing it and it's going okay, but it's going somewhat slowly and it's a live talk with not that much time. So you're like, all right, well, let's add some more workers to it. And while the computation is running, you add like 10 more workers or something. And it just on your cool Bokeh graph and everything, you just see it ramp up and take off. And so you can dynamically add and remove these workers to the cluster, right?
Yeah, definitely. So Dask does all the things you'd expect from any modern distributed system. Handles resilience, handles dynamically adding things. You can deploy it on any common job scheduler. So it does sort of all the things that you'd expect from something like Spark we mentioned before, or TensorFlow or Flink, or any of the sort of popular distributed systems today, but it does sort of just those things. So you can sort of sprinkle in that magical dust into existing projects. And that's really the benefit. Yeah. So we focus a lot on how do we add clusters efficiently, or how do we add workers to a cluster dynamically?
Yeah, it seems really useful. Just as you're doing more work, you just throw it in. And I'm guessing these clusters can be long-lived things and different jobs can come and go. And are they typically set up for like research groups or other people in longer term situations, or are they like sprung up out of Kubernetes, like it burst into the cloud and then go away?
I'm going to say both, actually. So what we'll often see is that there'll be an institution which will have something like Kubernetes or Yarn or Slurm, and they'll give their users access to spin up these clusters. So an analyst will sit down at their desk, they'll open up a Jupyter Notebook, they'll import Dask, use one of the Dask deployment solutions to ask for a Kubernetes Dask cluster. Then like their own little scheduler and workers will be created on that machine, on that cluster. They'll do some work for an hour or so, and they'll go away, and that cluster will go away. What IT really likes about this sort of adding and removing of workers is that we can add and remove workers during their computation. So previously, they would go into the cluster, they'd ask for, hey, I want 100 machines. They'd use those machines for like a minute while they loaded their data, and they would stare at a plot for an hour. And so it's not so much the ability to add new workers, it is the ability to remove those workers when they're not being used. This gives like really good utilization. You can support a lot more people who have really bursty workloads. So a lot of data scientists, a lot of scientists, their analysis is very bursty. They do a bunch of work and then they stare at their screen for half an hour. They do a bunch more work and they stare at the screen for half an hour. And so that sort of dynamism is really helpful in those sorts of use cases.
Yeah, I can imagine. That's super cool. Now, we talked about the Dask data frame and Dask array, and those being basically exact parallels of the NumPy and pandas version. But another thing that you can do is you can work in a more general purpose way with this thing called a delayed and a compute, right? Which will let you take more arbitrary Python code and fan it out in this way, right?
Yeah. So let me first add a disclaimer. Dask data frame and Dask array are not exactly like NumPy and pandas. They're just very close. Close enough, you'll be fine.
Similar, okay.
If I don't say that, people will yell at me afterwards. So the creation of Dask delayed was actually really interesting. So when we first built Dask, we were aiming for something that was Spark-like. Like, we're going to build this like very specific system to parallelize NumPy and parallelize pandas, and that'll handle everything. Everyone was built on top of those things. That did not end up being the case. Some people definitely wanted parallel pandas and parallel NumPy, but a lot of people said, well, yeah, like I use NumPy and pandas, but I don't want a big NumPy and pandas. I'm using something that's like really different, really custom, really bespoke. And they wanted something else, as though we had built like a really fast car. And they said, great, that's a beautiful car. I actually just want the engine because I'm building a rocket ship, or I'm building a submarine, or I'm building like a mechatronic cat or something. It turns out that like in the Python space, people build like really diverse things. Like Python developers are just on the forefront. They're doing new things. They're not solving the same classic business intelligence problem over and over again. They're building things that are new. And so Dask Delayed was like a really low-level API where they could build out their own task graphs, their own parallel computations, sort of one chunk at a time using normal Python for loops. So it allows you to build like really custom, really complex systems with normal-looking Python code, but still get all the parallelism that Dask can provide. So you still get the dashboard, you still get the resilience. You can build out your own system in that way.
Yeah, you even have the graph in the dashboard, as you said, which is really cool.
Yeah.
I love it. So when I saw that, I was thinking, well, this is really interesting, and I see how that lets me solve a more general numerical problem. Could I solve other things with it, right? Like suppose I have some interesting website that needs better performance, or I've got something that has really nothing at all to do with computation. Maybe it talks to databases or other things. Right. Could I put a Dask backend on like a high performance website and get it to do, bizarre cluster computations to go faster? Or is it really more focused on just data science?
Yeah, so people would use Dask in that setting in the same way they might use like a multiprocessing pool or a thread pool, but they would then or Celery maybe, but they would scale it out across a cluster. So Dask satisfies like the concurrent futures interface if you use concurrent futures. It also does async await stuff. So people definitely integrate it into systems like what you're talking about. I think at UC Berkeley there's a project called Cesium that does something like that. I gave a talk at PyGotham like a year or two ago that also talked about that. So yeah, like people definitely integrate Dask into more webby kinds of systems. It's not accelerating the web server. It's just accelerating the sort of computations that the web server is hosting. It's useful because it has like millisecond latencies and scales out really nicely and is like very Pythonic. It fits all the Python APIs you'd expect.
Yeah, and the fact that it implements async and await is super cool. If you use it with something like Sanic or Court or one of these async-enabled web frameworks, it's just a line, await some execution, and the scalability, spreads maybe just some Dask Kubernetes cluster or something. That's pretty awesome. You talked about the latency, and I was pretty impressed with how those were working. You were quoting some really good times. And actually, you said that's one of the reasons you created your own scheduler and you didn't just try to piggyback on Spark, is because you needed extremely low latency because it's kind of chatty, right? If I'm going to take the dot product of a thing that's all over the place, they've got to coordinate quite a bit back and forth, right? That can't be too big.
Yeah, so Spark actually internally has okay latencies today. It didn't at the time, but they're also at sort of the millisecond range. Where Spark falls down is in complexity. They don't handle sort of arbitrary task graphs. Sort of the other side of that is systems like Airflow, Luigi, and Celery, which can do more arbitrary task graphs. You can say, download this particular file, and if it works, then email this person, or if it doesn't work, parse this other thing. You can build all these dependencies into Airflow, Luigi, Celery. Where those things fall down is that they don't have good inter-task communication. So you can't easily say, I've got these two different pandas data frames of different machines, have them talk to each other. They don't handle that. They also have long latencies in sort of the tens of hundreds of milliseconds, which can be...
Right, which is not that long, but when you amplify it across, 1,000 times, then all of a sudden it's huge.
Yeah, or when your pandas computations take 20 milliseconds or 1 millisecond, and you want to do millions of them, then suddenly latency does become a big issue. So we needed sort of the scalability and performance of Spark with the sort of flexibility of Airflow, Luigi, Celery. And that's sort of where Dask is sort of that mix between those two camps.
This portion of Talk Python to Me is sponsored by Backlog from NewLab. Developers know the importance of organization and efficiency when it comes to collaborating on a team. And Backlog is the perfect collaborative task management software for your team. With Backlog, you can create tasks, track bugs, make changes, give feedback, and have team conversations right next to your code. You track progress with features like Gantt and burndown charts. You document your processes right alongside your wikis. You can integrate with the tools you use every day like Slack, Jira, and Google Sheets. You can automatically register issues from email or web form submissions. Take your work on the go using their top-rated mobile apps available on Android and iOS. Try Backlog for your team for free for 30 days using our special URL at talkpython.fm/backlog. That's talkpython.fm/backlog. I was really impressed with the low latency that you guys were able to achieve. And so maybe that's a good way to segment over to some of the internal implementations. You talked about using Gevent, Tornado. What are some of the internal pieces that are at work there?
Yeah, so on the distributed system, we use Tornado for concurrency. This is because we were supporting both Python 2 and 3 at the time. As Tornado is becoming more async I/O friendly, that's sort of becoming more common. So Tornado for concurrency, also Tornado a little bit for TCP communications, although we've had to improve Tornado's bandwidth for high performance computers.
That's cool. So has Tornado gotten a little bit better because you guys have been pushing it to the limits?
So
that's good.
Yeah, Dask touches a ton of the ecosystem. And so Dask developers tend to get pretty comfortable with lots of other projects. So Antoine Pitrou used to work on Dask a lot. He did a lot of the networking stuff in Python, and he also worked on Tornado and did lots of things. So he was handling that. So yeah, Tornado for concurrency and TCP communication. So all the Dask workers are TCP servers that connect to each other. So it's kind of like a peer-to-peer application. A bunch of just raw, basic Python data structures for our internal state, just because those are the fastest we can find. The Python dictionary is actually a pretty efficient data structure. So that's how we handle most of the internal logic. And then for computation, if you're using Dask data frame, we're using pandas for computation. If you're using Dask array, we're using numpy for computation. So we didn't have to rebuild those things. And then, compression libraries, encryption libraries, Kubernetes libraries. There's sort of a broad set of things we end up having to touch.
I can imagine. Is the cluster doing HTTPS or other types of encrypted communication and stuff like that between the workers and the supervisor?
Yeah. So not HTTPS. HTTP is sort of too slow for us. We tend to use TCP.
Okay.
Dask does support TLS out of the box, or SSL, you might know it as. But the comms are also pluggable. So we're actually looking at right now a high-performance networking library called UCX to do InfiniBand and other stuff. Security is standard in that way, assuming you're happy with TLS.
Yeah. I suspect most people are until the quantum computers break it, and then we have a problem.
Comms are extensible. We can we can add something else.
Quantum safe algorithm. Then yeah, I suspect we're going to be scrambling to solve the banking problem and e-commerce problem faster first, though. That'll be where the real fear and panic will be. But luckily, that's not here yet. So it just sounds like you guys are really pushing the limits of so much of these technologies, which sounds like it must be a lot of fun to work on.
Yeah, it's been a wild ride.
I can imagine.
Yeah, it's actually been interesting also building conventions and protocols among the community. I think Dask is at an interesting spot because we do talk to everybody. We talk to most scientific disciplines, we talk to banking, we talk to Fortune 500 companies, and we see that they all have kind of the same problems. So I think recently I put together a bunch of people on file formats, not because I care deeply about file formats, because I had talked to all of them. We also talked to all the different library developers, and it's really interesting to see, okay, Tornado 4.5, are we ready to drop it or not, for example? And we talked to the Bokeh developers, the Jupyter developers, the Dask developers, the Tornado developers. It's a well-integrated project into the ecosystem. I want to sort of hang there for a moment and say that because again, Dask was designed to affect an ecosystem, move an ecosystem forward. It actually has like its sort of tendrils into lots of different community groups. And that's been a really fun thing to see. Sort of not on a technological side, just on a social side, it's been very sort of satisfying and very interesting to see all these different groups work together.
Yeah, I can imagine you get to work with not just the library developers on all the different parts of the ecosystem, but you're also on the other side of the scientists and the data scientists and people solving really cool problems, right?
You'd be amazed how often like climate scientists and quantitative traders have exactly the same problems.
That's something I noticed doing professional training for 10 years. I taught a class at Edwards Air Force Base. I taught one at a hedge fund in New York, and I taught one at a startup in San Francisco. And like 80%, that's the same. It's all the same, right? Like it's good computation. It's algorithmical thinking. It's like distributed systems. And then there's the special sauce that probably I don't even understand anyway, right? But it's super interesting to realize that how similar these different disciplines can be.
Yeah. And from an open source standpoint, like this is new because previously all those domains had like a very different technology stack. Now they're all using the same technology stack. And so as a person who sort of is paid to think about software, but also cares about advancing humanity, it's like a really nice opportunity, right? We can take all this money from these quant traders, build that technology, and then apply that technology to genomics or something.
Right. Or climate science or something that like really needs to get it right quickly.
That's sort of a nice opportunity that we have right now, especially in Python, I think, that we can hire a bunch of people to do a bunch of good work that advances humanity. Also helps people rich, makes people be rich playing the stock market. But, we can let that happen.
Hey, yeah, if they're helping drive it forward, it might be okay.
Sure.
For the good, maybe. That's debatable, but probably. It sounds like such a cool project. Maybe let's talk a little bit more of the human side of it. Like, obviously, you work a lot on it, as you said, but who else? Like, are there a lot of people that maintain Dask, or what's the story there?
I've worked on it for a while so we started within Continuum, or what is now called Anaconda. And there's a bunch of other engineers within Anaconda who also work on Dask. They do sort of half-time something else and half-time work on Dask.
Are they still?
Definitely. People like Jim Christ, Tom Augsburger, Martin Durant, and others throughout the company. And so, they'll maintain various parts of the project or push it forward. So like Jim recently has been working on making Dask easier to deploy on Hadoop or Spark systems using Yarn. And that's something that is important for Anaconda's business, and it's also just generally useful for people. So there's a sort of nice overlap between helping out the open source project and also getting paid to do the work.
Yeah.
Outside of Anaconda, so I'm now at NVIDIA, and there's a growing group at NVIDIA who's also working on Dask, which is pretty exciting. And also there's a bunch of other people who are working in other research labs or other companies who need to use Dask for their work, and you need to build out the Kubernetes connection or something like that. And they maintain that both because it's good for their company and also they just sort of enjoy doing that. So I would say in sort of the periphery of Dask, most of the work is happening in other companies and other people. And there's, hundreds of people who do work on Dask in any given month or two.
There's probably a lot of people that make like one or two little contributions to like fix their edge case, but it all adds up, right?
There's that. There's also maybe like 20 or 30 people who are maintaining, not just adding a fix, but like maintaining some Dask foo package. So there's a researcher, Alistair Miles, who works in the Oxford area, who works on genomics processing, and he has like a Dask-enabled genomics suite called Scikit-Allele. And so that's his job, right? So he's working on that day to day. There's, the scikit-learn developers maintain the Dask scikit-learn connection through joblib. So Olivier Grisel has commit rights over all of Dask. He's a main scikit-learn contributor. So there's a bunch of sort of, as Dask expands out into the rest of the ecosystem, that it's sort of being adopted by many, many smaller groups who are in other institutions.
So it sounds to me like there might be some decent opportunities for folks to contribute peripherally to Dask in the sense that, maybe there's somebody that's doing some kind of research and their library or something like it would really benefit from having a Dask level version of that. So if people are looking to contribute to open source in the data science space, are you guys looking for that kind of stuff?
Yeah, definitely. I mean, you don't have to look these days. People are just doing it. What I would say is that there's probably, in whatever domain you're in, there's probably some group that's already thinking about how to use Dask in that space, and jump onto that group. There's a lot of sort of like low-hanging fruit right now. Pick your favorite PyData library. Think about how it could scale. And there's probably some small effort around that currently. And there's a lot of, if you want to get into open source, it's a great place to be. You're like right on the very exciting edge of big data and scalability. Things are pretty easy today. We've solved a lot of the major issues with sort of the core projects like NumPy and pandas and scikit-learn. So there's a ton of pretty exciting work that's like just starting to pick up now. So yeah, if you're interested in open source, it's a great place to start.
It seems like there's so many data science libraries that there's probably a lot of opportunity to like bring some of them into the fold. Pretty low hanging fruit there. So let me ask you some kind of how wild is that type of thing. One is, what's the biggest cluster you've ever seen it run on?
The biggest I've had
or heard about it running on?
Yeah. I would say like 1,000 machines is probably the biggest that I've seen. And that's probably like with an order of magnitude of limits today. But those machines are big machines. They have like 30 cores on them.
Yeah.
Like that's also just mostly for benchmarking. Like most problems in data science aren't that big.
Right.
Thousands is sort of a...
That's awesome. I was thinking of places like CERN that have their big grid computing stuff and things like that. They could potentially spin up something pretty incredible.
Dask gets used, I would say, on a fair number of supercomputers today, but it's very, very rarely used on like the entire supercomputer. There's really no system outside of MPI that I would expect to run on the full like CERN federated grid. So most of the sort of data science-oriented libraries end up sort of maxing out around 1,000 machines. I mean, hypothetically, you go higher, but the overheads will be enough to kill you.
Does it have a sort of a, like, how many people's hands you have to shake everyone's hand in a group? You know, like that in factorial type of issue. As you add more, does it get like harder and harder to add the next worker to the cluster, or is it okay?
No, it's fine. Everything's linear in terms of number of workers. Workers aren't, it's not like a mesh grid. It's workers talk to the scheduler to find out who they have to talk to. They'll then peer-to-peer talk to those people. But in any given computation, you only talk to 5 to 10 people at once.
Okay.
It's fine.
Yeah, interesting. Okay, the other one is, what's the coolest thing that you've seen computed or run on Dask or built with Dask?
I'm going to say, things I can't talk about, but
some are the most amazing ones are super secret.
I'm going to point people to the Geo Project. So this is actually my most recent PyCon talk in 2018, talking about other people's work. So Geo is pretty cool.
Mm-hmm.
Geo is a bunch of Earth scientists who are doing climate change, meteorology, hydrology, figuring out the Earth. And they have these, 100 terabyte, petabyte arrays that they're trying to work with. They haven't quite gotten to the petabyte scale yet. And yeah, so they usually set up something like Jupyter Hub on either a supercomputer or on the cloud in Kubernetes. They then analyze tens or hundreds of terabytes of data with Xarray or Dask array under the hood and get out, nice plots that show that indeed sea levels are rising. I think it's pretty cool in that it's good community of people. So there's like a bunch of different groups, NASA, universities, USGS, UK Met Office, anyone who's looking at large amounts of data, companies, plant labs, etc. So it's a good community. They're like figuring out how to store one copy of the data in the cloud and then have everyone compute on that using cool technologies like Kubernetes. They're inventing cool technologies like how do we store multidimensional arrays in the cloud. So yeah, like that's maybe a good effort. Not necessarily a cool computation, like from a Dask perspective, it's actually pretty like vanilla, but it's cool to see a scientific domain advance in a significant way using some of these newer technologies like Jupyter Hub and Dask and Kubernetes. And I'd like to see that repeated. So I think we could do the same thing with medical imaging and with genomics. So that's maybe like a cool example. It's not so much a technical situation, it's a community situation.
Yeah, well, it sounds like a cool example that could be just replicated across verticals.
Definitely.
Right?
We're starting to see that, which is really exciting.
Okay, that's great. So when I was looking into Dask, I ran across some other libraries that are like kind of like you described, Dask Foo. So there was Dask CUDA, Dask ML, Dask Kubernetes. Do you want to just talk a little briefly about some of those types of things and why you might use them?
I'll go in reverse order. So Dask Kubernetes is a library that helps you deploy Dask clusters on Kubernetes.
So you point it at like a Kubernetes cluster and you say, go forth and use that, and it could just create the pods and run them and all that?
Definitely. So it creates pods for all the workers. It manages those pods. If you ask it, there's like little buttons you ask it to scale up or scale down, and it'll manage all that stuff for you using the Kubernetes API. It presents users with like a super simple interface. They can open up a Jupyter notebook and just sort of play around. So that's what that does. And it has peers like Dask Yarn for Hadoop Spark clusters and Dask Job Queue for more high-performance computing schedulers like Slurm, PBS, SGE, LSF. So that's Dask Kubernetes. That's like on the deployment side. Dask ML is an effort to... There were a lot of sort of interesting ways of using Dask with machine learning algorithms, things like GLMs, generalized linear models, XGBoost, scikit-learn. That were all different technical approaches. And Dask ML is like almost like a namespace library that collects all of them together, but also using the sort of scikit-learn style APIs. So if you like scikit-learn and you want to scale that across a cluster, either with simple things like hyperparameter searches or with large data things like logistic regression or XGBoost, you should look at Dask ML and it'll help you do that. Dask CUDA that's like a new thing I've been playing with since moving to NVIDIA. People have been using Dask with GPUs for a long time, and they've developed like a bunch of weird, wonky scripts to like set things up just the right way. There were a ton of these with NVIDIA when I showed up. It's just a few like nice, convenient Python ways to set up Dask to run on either one machine with many GPUs or on a cluster of machines with lots of GPUs, and how to make that easy. So it's kind of like Dask Kubernetes in that it's about deployment, but it's more focused on deploying around GPUs. And there are some intricacies to doing that well.
I imagine you can scale like crazy if you put the right number of GPUs on a bunch of machines and let it go.
No, GPUs are actually pretty game changing. It's fun.
Yeah. It's kind of near the limits of human understanding to think about how much computation per second happens on a GPU.
I think CPUs are also well beyond the limits of human understanding.
But this is like the galaxy versus the universe, like
Sure.
They're both outside of our understanding.
I should mention that I work for NVIDIA now, so please don't trust anything I say. But yeah, GPUs are like fundamentally like a game changer in terms of computation. Like you can get a couple orders of magnitude performance increase out of the same power, which I mean, from like a science perspective, like has the opportunity to unlock some things that we couldn't do before. GPUs are also notoriously hard to program, which is why most scientists don't use them. And so that's sort of part of why I work at NVIDIA today. They're building out a GPU data science stack, and they're using Dask to parallelize around it. And so it's fun to see, it's fun both to sort of grow Dask within NVIDIA and have another large company behind it. But also from a science perspective, like I think we can do some good work to improve accessibility to different kinds of hardware like GPUs that might dramatically change the kinds of problems that we can solve, which is exciting in different ways.
Yeah, very incredible. And I would much rather see GPU cycles spent on that than on cryptocurrency.
Sure.
Although cryptocurrency is good for NVIDIA and all the GPU, the graphics card makers, they don't seem as useful as like solving science problems on them. All right, we're getting close to our time that we have left. So I'll ask you just a couple of quick questions before we wrap it up. So we talked about where Dask is. Like, where's it going? It sounds like there's a lot of headroom for it to grow. And NVIDIA is investing in it by sort of this work that you all are doing. And it sounds like they're also building something amazing. So yeah, what's next?
And maybe NVIDIA aside for a moment, I'll say that Dask technologically is sort of done. The core of it, there's plenty of bugs and plenty of features we can add, but we're sort of at like the incremental advancement stage. I would say where I'm seeing a lot of change right now is in broadening it out to other domains. So I mentioned Pangeo a little bit before. I think it's a good example of Dask spreading out and solving a particular domain's problem. And we're seeing, I think, a lot more of that. So I think we'll see a lot more social growth and a lot more applications to new domains. And that's really what I'm pretty excited about.
That's cool. So it's like Dask is basically ready, but there's all these other parts of the ecosystem that could now like build on it and really amp up what they're doing.
Yeah, let's go tackle those. Let's go look at genomics.
Yeah,
let's go look
sure.
at imaging. Let's go look at medicine. Let's go look at all of the parts of the world that need computation on the large scale, but that like didn't obviously fit into the sort of Spark, Hadoop, or TensorFlow regime. And Dask, because it's more general, can probably handle those things a lot better.
Yeah, it's amazing. I guess let me ask you one more Dask question before we wrap it up real quick. So is Dask 100% Python?
The core parts, yeah.
Or near?
Yes. You're probably also using NumPy and pandas, which are not Python.
Which, yeah, right, as we discussed. But yeah.
Dask itself is pure Python.
I think it's really interesting because you think of this like really high performance computing sort of core, right? And it's not written in Go or C, but it's written in Python. And I just think that's an interesting observation, right?
Python is actually not that bad when it comes to like core data structure manipulation, tuples, lists, dictionaries. It's maybe like a factor of 2 to 5 slower, not 100 times slower. And it's also not that bad at networking. Like it does that decently well. Socially, the fact that Python had both a data science stack and a networking stack in the same language made it sort of the obvious right choice. That being said, I wouldn't be surprised if in a couple of years we do rewrite the core bits in C++ or something. But we'll see.
Sure, eventually. When it's kind of finally baked and you're looking for that extra 20, 30% here or there, right?
Yeah, we'll see. We haven't yet reached the point where it's a huge bottleneck to most people. But like the climate science people do have petabyte arrays, and sometimes a scheduler does become a bottleneck there.
Right. It's cool. It's interesting. So final 2 questions. If you're going to write some Python code, what editor do you use?
I use Vim, not for any particular reason. I just showed up at the computer lab one day and said, how do I use Linux? And the guy there was a Vim user, so now I'm also a Vim user. I think I haven't moved off just because I'm so often on other machines. So like rich editors just don't move over as easily.
Yeah, I'm on the cluster. I need to edit something. It doesn't work to fire up PyCharm and do that so easily.
Right. Yeah. So Vim for now, but not religiously. Just anecdotally.
Sure. Sounds good. Yeah, I'm sure you do some stuff with Jupyter Notebooks as well every now and then.
Sure. I'll maybe also put a plugin for Jupyter Lab. I think everyone should switch from the classic notebook to Jupyter Lab, especially if you're running Dask, because you can get all those dashboards inside Jupyter Lab really nicely. It's a really nice environment.
Oh, yeah. That sounds awesome. All right. And then notable PyPI package. I'll go ahead and throw pip install Dask out there for you.
So I'll cheat a little bit here. I'm going to list a few. First, in a theme of the NumPy space, I really like how NumPy is expanding beyond just the NumPy implementation. So there's CuPy, which is a NumPy implementation on the GPU. There's Sparse, which is a NumPy implementation with sparse arrays. And there's Aura, which is a new datetime dtype for NumPy. I like that all of these were built on the NumPy API, were built outside of NumPy. I think that kind of heterogeneity is something we're going to move towards in the future. And so it's cool to see NumPy develop protocols and conventions that allow that kind of experimentation. And it's cool to see people picking that up and building things around it. So that's pretty exciting.
Those are great picks. It's cool that I learned one API and now I can do other things, right? Like I know how to do the NumPy stuff, so now I can do it on a GPU.
Right. Or I've got my NumPy code. I want to have better date times. I can just add this new library and suddenly all my NumPy code works. We get that sort of extensibility, which is something that we need, I think, going forwards.
Yeah, absolutely. All right, Matthew. Well, this was super interesting. Thank you for being on the show. You have a final call to action. People want to get involved with Dask. What do they do?
Try it out. You should go to examples.dask.org. And there's a launch binder link on that website. If you click on that link, you'll be taken to a Jupyter Lab notebook running in the cloud, which has everything set up for you, pretty much of examples. So you can try things out, see what interests you, and play around. So again, that's examples.dask.org.
Yeah, and also link to the Dask examples GitHub repo that you have on your account in the show notes. Yeah, so people can check that out too. Awesome. All right. Well, thank you for being on the show. It was great to chat with you, and keep up the good work. It looks like you're making a big difference.
Great. Thank you so much for having me, Michael. Talk to you soon.
Yep. Bye. This has been another episode of Talk Python to Me. Our guest on this episode was Matthew Rocklin, and it's been brought to you by Linode and Backlog. Linode is your go-to hosting for whatever you're building with Python. Get 4 months free at talkpython.fm/Linode. That's Linode. With Backlog, you can create tasks, track bugs, make changes, give feedback, and have team conversations right next to your code. Try Backlog for your team for free for 30 days using the special URL talkpython.fm/backlog. Want to level up your Python? If you're just getting started, try my Python Jumpstart by Building 10 Apps course. Or if you're looking for something more advanced, check out our new async course that digs into all the different types of async programming you can do in Python. And of course, if you're interested in more than one of these, be sure to check out our Everything Bundle. It's like a subscription that never expires. Be sure to subscribe to the show. Open your favorite podcatcher and search for Python. We should be right at the top. You can also find the iTunes feed at /iTunes, the Google Play feed at /Play, and the direct RSS feed at /RSS on talkpython.fm. This is your host, Michael Kennedy. Thanks so much for listening. I really appreciate it. Now get out there and write some Python code.